find a vector orthogonal to u and v. Okay, when you get directions that say find a vector orthogonal to, then you should think, oh, that means I'm supposed to find the cross product of those two vectors, because that's what a cross product does. Right? These two vectors are two vectors in space. One's pointing in one direction, one's pointing in another. They lie in the same plane, whatever that plane is. And when you take a cross product, you should get a third vector, which is perpendicular to both of the original vectors. Right? Again, so when you see these directions, find a vector orthogonal to, that's what it's asking. So then that brings up, how do we do a cross product? So let me set this up. The way we write cross product is like that. U, and it's a capital X, or some kind of an X in between that. You almost think that looks like multiplication. But remember that when we did the dot product, the dot between the two vectors also looked like multiplication. So these are not really multiplication. They are their own vector operations. But the way to do this, we need to write the two vectors in component form, one on top of the other. And it must be that the first vector, u, is on top. So let me write it down. 7, -14, 5. And the second vector is 14, 28, -15. So remember how we do cross product. A cross product, we're going to do something that we did with matrices, which is when you find the determinant of a 2 by 2 matrix, you do A times D minus B times C, right? It's along the diagonals. A times D minus B times C. Okay, well, we're going to be doing the same thing to find our component form of a cross product vector, right? The first component, I will cover up the first component of both vectors. And this 2 by 2 matrix, which is left, right here, I do this determinant operation. -14 times -15 minus 5 times 28. Right? This times this minus this times this. So these numbers are fairly big, so I'm going to do this all on my calculator. -14 times -15 minus 28 times 5. And I got 70. Okay, to find the second component, I'm going to cover up these two, and then I'm going to do the same determinant operation that I just did. 7 times -15 minus 5 times 14. The only thing is for the middle component, there is a minus in front of it. So let's do the same operation. 7 times -15 minus 5 times 14. 7 times -15 minus 5 times 14. -175. But again, because of that turns the negative into a plus 175. And the last component, again, cover up the last component of the two vectors and then do the determinant. Do the determinant 7 times 28 minus -14 times 14. 7 times 28 minus -14 times 14. 392. So this vector should be orthogonal to the original two vectors. Now, how could you tell for sure? You could do the dot product. with either one of these. 7 times 70 plus negative 14 times 175 times 5 times 392, or plus 5 times 392. You should get 0. Let me try it just for the first one. 7 times 70 plus negative 14 times 175 plus 5 times 392. 0. So that's what you expect, right? That's how you show vectors are orthogonal. So if you do the dot product between this and this, you should get 0. And I did.